Our last theoretical result is of somewhat different flavor, dealing with the analysis of the rate of decay of the residual in the matching pursuit. Recall the matching pursuit algorithm. The residual at the kth stage is given by b minus a times xk. However, due to the way matching pursuit updates its solution, this also equals a times xk minus 1 minus some coefficient multiplying the kth chosen atom. This coefficient is nothing but the inner product between the previous residual and the newly chosen atom. Observe that in this expression b minus a times xk minus 1 is the previous residual. Thus we obtain a very interesting recurrent formula for how the residual evolves over the iterations for the matching pursuit algorithm. Our goal now is to investigate how the norm of this residual descends as we iterate. As we have already mentioned, this is somewhat different from the kind of analysis we have been showing so far. We have chosen to present this result due to its elegance and relevance. By the way, the origin of this is a paper from 1993 by Mala and Zhang that introduced matching pursuit. So let's apply a few steps of algebra here in order to see how this norm changes over the iterations. This is the relation we have just exposed. Let's take a squared norm over both of its sides. Opening the L2 expression on the right, we get these three terms. Notice that we exploited the fact that the atoms are normalized. The second and the third terms can be merged, and we get this simplified expression. Now recall that when choosing the atom I0, we actually searched for the one that maximized the inner product with a k-1 residual, which explains this alternative description of the recurrent formula. Put differently, the rightmost term can be written as A transpose times r k-1, followed by taking the L infinity over the resulting vector and squaring the outcome. We conclude that for the matching pursuit, the energy in Rk equals the energy in Rk-1 minus the squared L infinity of A transpose times Rk-1. In order to proceed from here, we should explore the last expression and understand its behavior. We present the following property of the matrix A, referred to as its minimal magnification factor, S of A. It is given by the minimal possible ratio between the L infinity of A transpose times V and the L2 norm of V itself. The definition given here puts squares on both the numerator and the denominator, and the reason for that will be clear shortly. Observe that if the nominator would have used an L2 norm, then S of A would have simply been the smallest eigenvalue of A transpose. Could S of A be 0? If A has more columns than rows, and it is a full rank matrix, this is impossible, since this would imply that A transpose times any vector V is always 0. Just to get a feeling towards this definition, what is S for the identity matrix? In this case, we are minimizing the squared ratio between L infinity and the L2 of any vector, and this result is well known, being 1 over n. We will not discuss how the minimal magnification factor S of A is calculated, and simply assume from here on that given A, we can get S of A. Let's see now how this can be used. We return to the recurrent equation that shows how the energy of the residual in the matching pursuit descends over the iterations. This is the relation we got, and we apply a trivial change of multiplying and dividing by the squared norm of the previous residual, and clearly this keeps our equation correct. Our next step is to replace the rightmost ratio by S of A, a fact that will necessarily increase the overall value of this expression, thus leading to an upper bound. The implication is that at each iteration, the residual norm squared is decreased by at least a factor of 1 minus S of A. Thus, if k iterations are applied, we get this exponential decay of the residual, and S of A dictates how fast this descent will be. Observe that the very first residual is nothing but our vector b. Here is our observation posed as a theorem, claiming at least an exponential decay of the norm squared of the residual, with the constant being 1 minus S of A. One implication of this result is that OMP and least squares OMP have the same property, since in every iteration their descent is necessarily more aggressive. More broadly, this result explains the tendency of greedy algorithms to lead to a sparse outcome, as after few steps the residual becomes small enough.